Discovery in quantum materials could make electronics 1,000 times faster. Introduction. In a groundbreaking development that could revolutionize the field of electronics, researchers at Northeastern University have discovered a method to change the electronic state of matter on demand. This significant breakthrough holds the potential to make electronics 1,000 times faster and more efficient than current technologies, which primarily rely on silicon components. The research team and their findings. The research was led by Alberto de la Torre, an assistant professor of physics at Northeastern University, with contributions from Gregory Fiete, a professor of physics. The findings were published in the prestigious journal Nature Physics. The team's work focuses on a quantum material known as 1θs2, which has shown the ability to transition between insulating and conducting states through a technique they have dubbed thermal quenching. Thermal quenching, a new technique. Thermal quenching involves a controlled process of heating and cooling that allows researchers to switch the material state from an insulator to a conductor and vice versa. This rapid state change can be achieved almost instantaneously, a capability that mirrors the function of transistors in modern electronics. The researchers have demonstrated that by applying light to the quantum material at near room temperatures, they can induce a hidden metallic state that was previously only stable at cryogenic temperatures. Implications for electronic devices. Current processors operate at gigahertz frequencies. However, the ability to utilize this new technology could propel operations into the terahertz range, vastly increasing the speed of electronic devices. This paradigm shift could lead to the replacement of traditional silicon components with smaller, faster quantum materials, potentially revolutionizing everything from smartphones to supercomputers. Fiete emphasized the significance of this research, stating, "Everyone who has ever used a computer encounters a point where they wish something would load faster. There's nothing faster than light, and we're using light to control material properties at essentially the fastest possible speed that's allowed by physics." Stability and longevity of states. One of the most impressive aspects of this discovery is the stability of the programmed states achieved with the quantum material. The material can maintain its conductive or insulating state for months, an unprecedented achievement in the realm of materials science. Previous research often relied on ultrafast laser pulses to induce temporary changes in material conductivity, which lasted only fractions of a second and typically required extremely low temperatures. Simplifying electronic design. Traditionally, electronic devices have required both conductive and insulating materials, along with a meticulously engineered interface between the two. The breakthrough achieved by de la Torre and his team simplifies this process by enabling a single material to perform both functions, conducting and insulating, controlled by light. This advancement not only streamlines the engineering process but also expands the range of operational temperatures at which the material can function. Fiete noted, "We eliminate one of the engineering challenges by putting it all into one material, which allows for a more efficient design framework in electronic components." The future of electronics and quantum computing. The implications of this discovery extend beyond just faster electronics. As Fiete pointed out, the density of logic components in current silicon-based semiconductors has led engineers to stack them in 3 dimensions, a practice that has its limitations. To achieve significant advancements in information storage and operational speed, a new paradigm is necessary, one that this research aims to address through innovative materials and quantum mechanics. The potential applications for this technology are vast. In addition to faster computing, it could lead to advancements in various fields, including telecommunications, data processing, and even quantum computing itself. The researchers are optimistic that their work will pave the way for future developments that will further integrate quantum materials into everyday technology. Conclusion. The research conducted by the team at Northeastern University marks a significant milestone in the field of materials science and quantum mechanics. The ability to control electronic states on demand not only holds promise for faster and more efficient electronics but also opens new pathways for innovations that could redefine how we interact with technology. As the demand for speed and efficiency in electronic devices continues to grow, discoveries like this will be crucial in shaping the future landscape of electronics and computing. This breakthrough is a testament to the power of scientific inquiry and its potential to create transformative technologies that could enhance our daily lives and drive progress in numerous industries. The future of electronics fueled by quantum materials looks brighter and faster than ever. The counterintuitive information in this content includes several surprising implications of the research findings. Here are the key points. 1. Switching between states. The ability to switch a material from an insulating to a conducting state, and vice versa, on demand is a significant departure from traditional electronics where materials have fixed conductive or insulative properties. This means that instead of needing separate materials for different functions, a single quantum material can perform both roles. Simplifying electronic design. 2. Use of light for control. The fact that light can be used to control the state of a quantum material is counterintuitive because it suggests that physical properties often thought to be static can be dynamically manipulated using electromagnetic radiation. This challenges conventional wisdom about material states being invariant unless subjected to physical alterations. 3. Operational temperature range. Achieving stable conductivity at near-room temperatures as opposed to previously required cryogenic temperatures is another unexpected advancement. This means that practical applications of these quantum materials could be realized in everyday electronics, which typically operate at ambient temperatures. For longevity of material states, the ability of the material to maintain its programmed conductive or insulative state for months is a significant leap from prior methods that produced only fleeting changes in conductivity. This longevity opens up new possibilities for the design and functionality of electronic devices. 5. Replacement of silicon. The prospect of replacing silicon components with quantum materials that are exponentially smaller and faster challenges the long-held belief that silicon will remain the dominant material in electronics. This suggests a potential paradigm shift in materials science and the future of technology. 6. Speed of operation. The potential to operate at terahertz speeds as opposed to the current gigahertz is a dramatic leap that could redefine performance metrics in electronics. It implies that the limits of speed in electronic devices, which have been considered nearly insurmountable, may be pushed much further. 7. Interface elimination. The research indicates that the need for well-engineered interfaces between different materials can be eliminated, which simplifies the design process and potentially reduces costs and manufacturing complexities. 8. Innovation in materials. The study highlights a new approach to solving limitations in current semiconductor technology, suggesting that innovation in materials rather than just in processing technology could yield the next major advancements in electronics. These points collectively demonstrate a significant shift in understanding how materials can be manipulated and utilized, suggesting that the future of electronics may be far more flexible and efficient than previously anticipated. The recent discovery by researchers at Northeastern University regarding the manipulation of quantum materials for electronic applications presents several significant insights that are often overlooked in broader discussions about advancements in technology. Here are some critical aspects of the report that merit closer examination. 1. The role of thermal quenching in material properties. One of the most striking elements of this research is the innovative application of thermal quenching to control the electronic states of materials. By utilizing controlled heating and cooling, the researchers can switch a quantum material between insulating and conducting states. This technique allows for immediate reversibility and, importantly, stable changes at near-room temperatures, a feat that has implications for the practicality of quantum materials in everyday electronics. Significance. The method of thermal quenching can reshape how we think about material properties and their applications. Traditionally, materials with distinct electrical properties require complex engineering to interface conductive and insulating materials effectively. The ability to manipulate a single material's state reduces the need for multiple components and interfaces, which simplifies design and manufacturing processes. This could lead to more compact and efficient electronic devices, ultimately making technology more accessible and affordable. 2. Potential for terahertz operations. The research highlights a shift from gigahertz to terahertz operations in electronic devices. Current processors operate in the gigahertz range. But the findings suggest that using this new quantum material could allow for operations at terahertz speeds. Significance. The implications of terahertz operations are profound. It suggests a future where data processing and transmission can occur at speeds that vastly exceed current capabilities, potentially leading to real-time processing of data that is currently bottlenecked by slower electrical components. This advancement could enhance everything from computing power to telecommunications and data storage systems, fostering innovations in fields reliant on high-speed data processing such as artificial intelligence, big data, and cloud computing. 3. Stability of the conductive state. Another critical point of the discovery is the stability of the hidden metallic state achieved in the quantum material 1θs2. Unlike previous studies where changes in conductivity were fleeting, this material maintains its programmed state for months. Significance. Stability is a crucial factor for any material used in electronics. The ability to maintain a conductive state over extended periods without requiring extreme conditions like cryogenic temperatures means that these materials could be integrated into consumer electronics without the need for specialized cooling systems. This stability not only enhances usability but also opens the door for commercial applications, thereby accelerating the adoption of quantum materials in practical devices. 4. Simplification of electronic design. The research proposes that the discovery enables the use of a single material that can serve both as a conductor and an insulator controlled by light. This eliminates the need for complex multi-material systems. Significance. This simplification could lead to a paradigm shift in electronic design, making it easier for engineers to create devices with fewer components. Reducing complexity can decrease manufacturing costs, improve reliability, and potentially lead to a new generation of devices that are smaller, lighter, and more energy efficient. Additionally, this could accelerate the pace of innovation in consumer electronics, as new companies may find it easier to enter the market with simplified production processes. 5. Implications for the future of silicon-based technologies. The ability to control material properties dynamically suggests a potential shift away from silicon-based technologies which have dominated the electronics industry for decades. Significance. Silicon's limitations are becoming increasingly apparent as we reach physical and thermal limits in miniaturization and efficiency. The discovery of new quantum materials that can outperform silicon could lead to significant advancements in electronic capabilities. This transition could not only enhance performance but also address the growing concerns over energy consumption and heat generation in electronic devices, paving the way for a more sustainable technological future. 6. Interdisciplinary impact and broader applications. The research's implications reach beyond just electronics. They could resonate through various fields such as quantum computing, telecommunications, and materials science. Significance. As the boundaries between different scientific disciplines continue to blur, advances in quantum materials could facilitate breakthroughs in quantum computing, an area that relies heavily on precise material properties for the development of qubits. Furthermore, the techniques developed in this research may be applicable in other areas such as energy storage, e.g. batteries and capacitors, and photonics, light-based technologies, signaling a cross-disciplinary revolution in how we design and utilize materials. 7. The importance of innovation in material science. Lastly, the research underscores a fundamental need for innovation in material science as a critical component of technological advancement. Significance. As technology demands increase, so does the need for novel materials that can meet these challenges. This discovery exemplifies how targeted research in material properties can yield significant benefits. It highlights the importance of supporting scientific inquiry in material science as a foundation for future innovations, ensuring that we are prepared for the next wave of technological advancements. In conclusion, while the core finding of the Northeastern University research, that quantum materials can be controlled to switch between conductive and insulating states, may seem straightforward, the broader implications of this discovery suggest a transformative potential for the future of electronics and other fields. Each of these overlooked aspects contributes to a more comprehensive understanding of how this research could influence technology industry practices and even the fundamental ways we approach scientific problems. The discovery by researchers at Northeastern University, which enables the electronic state of matter to be switched on demand, presents a transformative opportunity for the future of electronics. Here are the 4 most valuable points for in-depth analysis and discussion. 1. Revolutionizing speed and efficiency. The ability to switch between insulating and conducting states through a method called thermal quenching could increase the speed of electronic devices from gigahertz to terahertz. This leap in speed is not merely incremental, it represents a potential 1,000-fold increase in processing capabilities. Such advancements could enable faster data processing, more efficient computing operations, and the development of next-generation electronics that are significantly more capable than current silicon-based technologies. 2. Implications for material design. Traditional electronics rely on a combination of conductive and insulating materials, requiring complex interfaces between them. This research simplifies the design by allowing a single quantum material to serve both roles. Control through light. This breakthrough not only reduces the engineering challenges associated with creating these interfaces but also broadens the operational temperature range, making it more practical for real-world applications. The shift towards using quantum materials could lead to miniaturized devices that perform better while consuming less power, effectively changing the landscape of electronic design. 3. Stability of quantum states at practical temperatures. The successful manipulation of the quantum material 1θs2 to achieve a hidden metallic state at near-room temperatures is a significant advancement. Previously, such states were only achievable at cryogenic temperatures, which limited their applicability. The fact that this new state can be maintained for months marks a crucial step towards practical use in electronic devices, potentially enabling long-term stability in applications that require consistent performance without frequent recalibration or temperature management. 4. Future of electronics and quantum computing. This discovery aligns with the broader push towards quantum computing and advanced materials that could redefine information storage and processing. As semiconductor technology approaches physical and practical limits, innovations like this could serve as a new paradigm in electronics, paving the way for devices that leverage the unique properties of quantum materials. The research highlights the ongoing need for innovation in materials science and the potential for quantum technologies to play a critical role in the evolution of computing and electronics, promising a future where devices are not only faster and smaller but also more efficient and capable of handling complex tasks. These points underscore the significance of this discovery in transforming the future of electronics, addressing both practical engineering challenges and theoretical advancements in quantum mechanics. 1. The invention of the transistor 1947. The development of the transistor by John Bardeen, Walter Brattain, and William Shockley at Bell Labs revolutionized electronics by allowing for the miniaturization of circuits and the creation of smaller, more efficient devices. Transistors replaced vacuum tubes, enabling faster and more reliable performance in radios, computers, and other electronic devices. This breakthrough laid the foundation for modern electronics and computing, similar to how the recent discovery in quantum materials at Northeastern University could transform electronic speed and efficiency. 2. The discovery of superconductivity 1911. Superconductivity was first discovered by Heike Kamerlingh when he observed that mercury exhibited zero electrical resistance at temperatures close to absolute zero. This phenomenon opened the door to a range of technological advancements, including magnetic levitation and MRI machines. The ability to manipulate material properties at low temperatures parallels the recent findings in quantum materials that allow for rapid switching between conductive and insulating states, suggesting new possibilities for efficient electronic devices. 3. The development of silicon integrated circuits. 1960s. The creation of silicon integrated circuits by Jack Kilby and Robert Noyce marked a significant milestone in the field of electronics. This innovation enabled the miniaturization of electronic components, leading to the widespread use of computers and consumer electronics. Just as silicon integrated circuits transformed technology by making devices smaller and more efficient, the recent breakthroughs in quantum materials could herald a new era of electronics, potentially replacing silicon and further enhancing speed and efficiency in electronic devices. The recent breakthrough in quantum materials by researchers at Northeastern University heralds a transformative era for electronics, potentially making devices 1,000 times faster and more efficient. This discovery, which allows for the on-demand switching between conductive and insulating states using a technique known as thermal quenching, has significant implications for the future of technology. Revolutionizing electronics. 1. Speed and efficiency. Current electronic processors operate at gigahertz frequencies. The new technology could enable operations at terahertz speeds, vastly improving processing power and efficiency. This leap in speed could redefine the capabilities of computers and mobile devices, making previously inconceivable tasks feasible in real time. 2. Replacing silicon. The ability to control material properties instantaneously with light suggests a future where traditional silicon components may be replaced with smaller, faster quantum materials. This transition could lead to the development of ultra-efficient electronic devices, paving the way for innovations in various fields including computing, telecommunications, and consumer electronics. Implications for quantum computing and materials science. 1. New paradigms in computing. As the limitations of silicon-based technology become more apparent, quantum materials offer a promising alternative. The research highlights the need for a paradigm shift in material design and electronics, potentially advancing the field of quantum computing. This new approach could lead to devices that not only process information faster but also store it more efficiently. 2. Stable conductivity switching. The achievement of stable conductivity switching at practical temperatures represents a significant advancement in quantum mechanics. Previously, similar effects were only observed at cryogenic temperatures and for very short durations. The ability to maintain these states for extended periods could facilitate the development of more reliable and robust quantum devices. Engineering simplifications. 1. Reduction of complexity. By enabling a single material to function both as a conductor and insulator, the need for complex interfaces between different materials is minimized. This simplification in engineering could lead to more compact and efficient device designs, reducing production costs and time. 2. Broader temperature range. The discovery allows for controlled switching across a wider range of temperatures, which is crucial for practical applications in everyday electronics. This adaptability could make quantum materials viable for use in various environments and conditions. Future outlook. 1. Market transformation. As industries begin to adopt these quantum materials, we can expect a significant shift in the electronics market. Companies that invest in this technology could gain a competitive edge, leading to rapid advancements in product capabilities and performance. 2. Integration into consumer electronics. In the near future, we might see smartphones, computers, and other consumer electronics powered by quantum materials, offering unprecedented speed and efficiency. This could lead to innovations such as instantaneous data streaming, real-time processing of complex algorithms, and advanced artificial intelligence applications. 3. Research and development. Ongoing research will likely focus on optimizing these quantum materials for commercial use. This includes improving their stability, scalability, and integration with existing technologies. Collaborations across academia and industry will be crucial in advancing this field. Conclusion. The discovery of controllable quantum materials represents a pivotal moment in the evolution of electronics. By enabling unprecedented speed and efficiency, this breakthrough not only challenges the dominance of silicon but also opens new pathways for innovation in computing and materials science. As researchers continue to explore these possibilities, the future of technology looks poised for remarkable advancements that could redefine our interaction with digital devices.